All right, ladies and gentlemen, welcome back to another video with Mr. Kenton for AP Chemistry. And we're continuing our discussion moving through the collision model. And the collision model is going to dive in a little bit more deeply into what we introduced in the previous video about elementary steps. And we talked about how bonds had to be broken and formed. But now we're going to get into, well, how do molecules, when they collide, when the bonds break, are there some other components that are going to influence that? And that's going to be called the collision model. And so we're going to talk about the factors that influence kinetics from this perspective using the collision model. So let's dive in. So what is it, right? And essentially what collision theory helps you and I to be able to do is to be able to explain why reactions occur at different rates, right? So we've got this experimental data that shows, hey, when the concentration is higher, the rate's faster, okay? Or we have information that shows, hey, when it's at lower temperature, hey, this reaction occurs slower. But that doesn't really tell us the why. It just gives us like a cause, right? And so this is going to try to give us the why as to what's going on here. And so for us, collision theory states three things have to happen in order for a reaction to take place, right? If one of these things is missing, a reaction cannot take place, right? And so the first thing that we notice is that the particles must collide, right? In order for a reaction to take place, the particles that are reacting have to collide with each other, okay? And so ultimately that's going to boil down into the frequency of the collisions is going to influence the rate. The second thing that we know has to happen in order for a reaction to take place is that the particles that are reacting or that are colliding have to have sufficient energy, right? It's this idea that if they don't have sufficient energy, they can't break the bonds that are there so that new bonds can be formed, right? And this is what we're going to commonly refer to as activation energy. And then the third thing that we know that has to be true within collision theory, and that helps us frame this, is that the molecules, when they collide, not only do they have to collide, not only do they have to have sufficient energy, but they also have to be in the correct orientation, right? And what that means is depending on what bonds need to be broken, the particles might need to be positioned in a very specific way so that when they collide, it leads to the bonds being broken and the new bonds being formed. And so we're going to dive into those three components of collision theory in more depth here on the next slides. Now, for the first one, I know there's a lot of information there, right? But what we need to understand is that in order for a reaction to occur, specifically if it's bimolecular and above, there needs to be collisions between our reactants, right? Now, I do want to go ahead and just note that if something is termolecular, so that component where we have three different molecules, whether they're all the same or if it's three different or two of the same and one different, collisions in termolecular processes are really rare. And like this piece about collisions helps us understand why, right? Because if you have to have three molecules that are hitting simultaneously in order to break bonds, that's going to be really difficult to control for and to account for. This is why they're so rare. Now, for us, when we start thinking about ways in which we can increase rate based on collisions, this is where that concentration piece is so important, right? If we want to increase the rate of an aqueous solution or gases, one thing we can do is simply increase the concentration, right? If we increase the concentration, that means that we have more of the aqueous solution or more of the gas particles that are available. So it gives more opportunities for them to react or for them to collide. Also for gases specifically, if you decrease the volume on your container, then what you're going to do is you're going to increase the concentration. And that's also going to limit the amount of space that the particles can move in. So collisions are going to occur more frequently. Certainly, you could also just simply add more of the substance, and that would do the same thing. Now, for the rates of solids or immiscible liquids, and remember, immiscible liquids means liquids that don't mix. What we would want to do is increase the surface area that's being exposed to the reaction medium, right? And obviously I'm about to list a process that isn't chemical in nature, but it should help us better understand this point, right? So let's think if we're trying to dissolve a sugar cube versus granular sugar itself, right? If you place a sugar cube in a liquid, it's going to take longer for the sugar cube to dissolve. But if you take just granular sugar, place it in a liquid, it's going to dissolve much more readily, right? And we could apply this maybe if you're doing a reaction with an acid and a metal solid. Like if you take granular metal, for example, and you reacted it with, let's say, an acid, it's going to react much more quickly. Whereas if you took a chunk, let's say that you took like mossy zinc, for example, and placed it in an acid, it would take longer for all of the zinc to be consumed because its surface area is much smaller. That's being exposed to the actual reaction medium. Now, the other thing that's going to influence collisions is going to be temperature, right? We know that temperature is a measure of average kinetic energy. So if we increase the temperature, what that's going to do is it's going to cause the particles to move faster. Well, if the particles are moving faster, it's going to cause an increase in the number of collisions, right? And so certainly changing the temperature is going to cause for more frequent collisions, more opportunities for reactants to be converted to products. And this is why we mentioned previously that K is dependent on the temperature, right? We can look at the same reaction at one temperature, its rate could be one thing, but at a higher temperature, maybe its rate's faster. And that's just accounting for the increased particle movement. And again, within this context, we're just thinking of ways in which we can increase the number of collisions, right? Because if we increase the number of collisions, we're increasing the likelihood of going to products. Now, on the flip side of that, we need to also recognize that not all collisions are going to lead to a reaction. And the reality is only a small fraction of those collisions actually lead to product formation. So I hope that makes sense about how collisions play into this particular piece and how we can increase the number of collisions by changing concentration, changing volume, changing surface area, or changing temperature. Those are really the four factors we can use to increase the number of collisions we have. Now let's look at activation energy. That's that second component of collision theory. So activation energy, E sub A, is defined as the minimum amount of energy needed for a process to start, and in our case, needed for the reactants to react, right? And I guess it's a classic example of explaining something from the perspective of like a roller coaster, for example. If you want a roller coaster to be able to get through all of the loops and all of the components of your track, you need to make sure that whatever your initial jump is, like your initial amount of potential energy you're storing in it, is enough to get you through the roller coaster, right? If you think about it, if you've ridden on a roller coaster, they always take you up to a really high point, and then you get dropped down, right? It's because they're trying to store up enough potential energy so that it can make it through the track. Well, the same thing is true with our reactions, right? If our reactants don't have enough energy, they can't react. They can't get over that hill, and the process doesn't proceed forward. Now, if you remember from kinetic molecular theory when we talked about gases, we know that as temperature increases, that the total kinetic energy increases within our system. Now, the other piece that's important here is that what's also going to happen is that the number of molecules with energy that's greater than the activation energy is also going to increase, right? Because we've increased total kinetic energy. It means we're increasing the energy that's there. That means the number of molecules that have increased energy goes up, which means you have more particles with more activation, an energy that's greater than the activation energy. And what we see here is that as long as the temperature is high enough and you have enough particles that are necessary to energy, that have enough necessary energy, then a reaction is going to take place and it's going to happen. It's going to keep proceeding forward. Now, obviously, if you run out of reactants, then it's not going to continue anymore. Now, if none of the particles have the correct activation energy, you might need to heat the sample so that it will have enough energy. Another possibility is maybe that it needs light energy to help kickstart it. Maybe it needs electricity to kickstart it. So you're going to have to find whatever it is that's going to help it get over that activation energy hump. Now, that doesn't mean that particles that don't have the right activation energy don't collide at all. It just means that when the collisions happen, they simply collide, but no bonds are broken, right? And that should make sense. Collisions are still going to happen. They just won't lead to product formation. And the last thing I think it's important to remember here is that when you're looking at your particles, you're going to have some that have enough energy to react. The reality is you're also going to have some particles that don't. And that's okay. That's to be expected because remember, temperature measures average kinetic energy. So you're going to get particles that are on a spectrum of energies. Same thing's true here when we're talking about activation energy. You're going to have some particles that have that minimum activation energy and some that don't. Now, we're going to revisit our good old friend, the Maxwell-Boltzmann distribution curve, right? And so you remember it talked about, we got kinetic energy on the x-axis, and we got the fraction of molecules that are on the y-axis. And we've got two curves here. Now, the only other thing that we need to understand is that there's this dotted line here, and we're stating that this is the minimum energy needed for the reaction to occur, right? And so anything that is before this dotted line doesn't have the minimum energy need required in order for this to happen. Anything that's past that line is going to have that minimum energy. And now we've got two curves that have been graphed here. We have one that's in blue and one that's in red. Now, obviously, they've told us one's lower and one's higher. But if we weren't told that information, we should be able to deduce that, okay, because the blue curve has less blue shaded in than our red curve has shaded in past that activation energy, that red would be at a higher temperature and blue would be at a lower temperature. Okay, so be sure that you can understand and explain what's going on here with that Maxwell-Boltzmann distribution curve. All right, the last component that we need to take a look at within collision theory is that orientation component. And so in order for a reaction to occur, the reactant molecules must collide in the correct orientation and with enough energy to form products. See, that's why those three pieces are so important. If you have just one of those things or two of those things and you don't have the right orientation, then it's not going to matter, right? So that's why this is such an important component to this theory or to this model that we're using. Now, let's say we take, it seems like a simple example. We got chlorine, free radical chlorine, reacting with NaCl to form nitrogen monoxide and chlorine, okay? Now, I'm going to present to you guys two ways that this could happen. One of them is effective, one of them is not, right? And then I also want you to think about when you look at the diagrams, there's another way that this could happen that would also be ineffective. And I want you to think, what would that look like? So here you go. So we've got our effective and our ineffective collision, right? So our effective collision is the one that's on the top. So the green spheres represent chlorine, blue spheres represent nitrogen, red sphere represents oxygen. So in our effective collision, notice that the chlorine atoms are coming together and they're about to collide with each other, right? Like it's evident here that what's going on is this chlorine atom is about to hit here, right? So the chlorine atom comes in, it hits.
Hey, Mr. Kenton.
And, we're able to go through and we're able to see that it reacted. So it collides, and then after the collision, the bond breaks between nitrogen and chlorine, and it's free to move on. In our ineffective collision,
Hi, Mr. Kenton.
What we have happening is we've got a collision between chlorine and oxygen and not chlorine and chlorine. So the collision happens, a bond doesn't form, and it just bounces off, right? That would be an ineffective collision. Now, were you able to think of, after looking at this, can you think of that other way that it could happen? I think if you take a look at it, what you'd find is if chlorine interacts with nitrogen, then that's not going to work, right? That would be the third way that this could happen, but it's going to be ineffective. All right, so that's kind of the last component that we needed to talk about with collision theory. And so just to kind of recap, we talked about one, like what collision theory is, that it's made up of 3 components. Part of it talks about collisions, activation energy, and orientation. We saw that there were several ways to increase collisions. We could change concentrations, we could change pressure, and we could change volume. For solids, we could change surface area. Think of granular versus like bulky. And let's talk about temperature. And then with activation energy, we talked about how you need to have this minimum energy needed to react. And so to increase activation energy, one thing you could do, or increase the number of particles that have that minimum activation energy, is raising the temperature. And then the last component is orientation, right? If you have the right energy and you have the collisions taking place but the wrong orientation, then products can't be formed. So I hope that this was insightful. If you do have any questions, please don't hesitate to ask. Make sure you fill out the Google form, and I look forward to seeing you guys again soon. Take care.